So I would like to start this video by answering some questions that I've gotten, and it's comments that I think have appeared numerous times. So I think it's about time to answer some of them. They are quite fundamental for the understanding of what we're talking about here. Alright, so the first question I saw was that someone wanted me to prove gravity. He said that you haven't provided any proof of gravity. Now, there's a fundamental problem about that notion that I need to prove gravity. And let me show you why. I'll take this, I have a eraser here, and then I'll say my hypothesis is that gravity, as it is, makes things fall to the ground. And then I take my eraser and do this. Alright, it fell to the ground. I have now proven gravity. Now the inherent problem with that notion is that science does not prove, because that can either be considered extremely easy. I just did it. I proved that my hypothesis was correct by showing that my eraser fell to the ground. Or it can be extremely impossible, because you can't really, how many experiments do you have to perform before you actually have proven something? So the notion in the current notion that we use in science is that we don't prove something, we actually try to disprove or refute a claim. And if a claim has survived several attempts to refute it, then it is quite possible that it will gain the status as what we call a theory in science. There's also another notion that a theory in science is not some wild random thought or something you can just come up with, like when you say, I have a theory about something. A theory in science is a collection of ideas that has been attempted to be disproven numerous times, like gravity, or for instance the new both Einstein's special relativity and now also the general relativity. We have numerous studies that show that these two concepts are probably most likely correct. Now that's another thing. In science we don't say this is right, even with gravity, but we say it's probable. It's highly probable that we have a force here on Earth and in the universe that we call gravity, and that it is best described by in our local on Earth and our local environment, best described by Newton's law. Let me just jot it up pretty quickly. So we have that the force is equal to big G m1 times m2 divided by the radius squared, if you can read it. So that is the main notion. Now the key question here is that these two, the masses, is a pretty constant. We can just measure them. We have a fairly good idea about that. The radius we can also measure, but this here, the gravitational constant, that is hard to measure actually, but it has been done. First of all, we have the Cavendish experiment. And like I said on the last video, someone asked, I think Brian Mullen actually asked, why the original experiment hasn't been performed yet, or haven't been tried to do it yet. And the idea of the Cavendish experiment has been tested numerous times, even by high school students. But the exact experiment that he did, because it was very expensive, he had to fortify those balls. He put up all those giant balls he put up in order to make sure that nothing else interfered, because the gravitational constant as we have it now is a force, I think it's 10 to the minus 6th. So that is an extremely low number, extremely low. So that is why it's very hard to measure. Alright. But so I won't and I can't prove gravity. But I can tell you that there's been numerous attempts to disprove the idea of gravity, and no one has come up with a viable solution yet. It still stands. Now, of course, this law I put up here by Newton in the overall universe, that is actually incorrect. The real deal that we are talking about is what we call Einstein's field equations. I'll see if I can remember in my head, but it's something like we have the Ricci tensor mu minus 1/2 r g nu. You can put the gravitational what's it called? The Einstein's constant in here. That would be this omega. I think it is g nu. Sorry, I reversed the indices, but and then it's 8 pi g, I think, over c square, and then this tensor here nu. So that's roughly how it looks. Now this is a tensor equation, so in reality you have 10 coupled equations that you have to solve, but in order to solve them, it's very hard to solve them. You put in different assumptions in order to reduce it. My field of study, gravitational lensing, is basic idea is about that. But let me just sort of give the whole main idea what is the difference between Newton's law of gravity and Einstein's law of gravity. Alright? So for Newton it is one and two. It is something that goes on between two objects with mass. For Einstein, it is more like you have a field like this. This is space-time. In space-time we have three coordinates for space, and then we have one coordinate for time. Now if you put a massive object in here, like the sun, then, see if I can draw it, it will sort of bend space-time around it downwards. So that is why if for instance you say that a photon comes close to a very massive object, you would say that a particle like that in motion will always try to follow a geodesic. So geodesic is the shortest route. Now in a flat space the shortest route is definitely a straight line, but in a curved space the shortest line will bend the particle. That is actually what you would say that my field of study, gravitational lensing, is all about. But I have put a timer so I can see how much time I have, so let's quickly move on. The next question is, why does gravity on a rotating Earth hold the air with no drag? That is a very hard question to answer, because the only answer we can give is that we can observe that there's no drag. But you can perform an experiment where you take a bucket of water like this and then put it on some machine that can make it rotate. I know this is the reverse example because here you have some surroundings with something in the middle. But what you can do is that you make this rotate, and then you would observe that the water inside slowly starts to rotate with the bucket, and eventually they will rotate with the same speed or velocity, angular velocity to be exact. Now what you can do in order to sort of more reproduce what goes on with Earth is that you stop this rotating machine, and then you stop the bucket and then release it again. And then you will see the bucket will begin to slowly rotate, unless the machine of course is breaking it, the rotation, but it will rotate with the bucket again. And that is probably why there's no drag between the air and the Earth. You have to remember that the Earth is almost 5 billion years old, so there's been plenty of time to make the air follow the Earth. Furthermore, the atmosphere following or moving with the Earth could also be a remnant from when the Earth was created. I would like to post a video later on how we think that Earth and the solar system was created. Alright, so the last thing, and I can see I have to be a little quick about it, is, and this has occurred many times, is how does gravity hold the oceans when a balloon can rise? In order to show you this, I would like to give two examples. Let's take the Pacific Ocean, call it PO, and then some balloon. Alright, so in order to find out we know that the force of gravity is on Earth is equal to F equals mg. So let's find the mass of the Pacific Ocean. Now I found that the volume, the mass can be calculated by saying that we have the density times the volume. So I found that the density of water is around 1,000 kilograms per cubic meter, and the volume, of the Pacific Ocean is around 666 billions kilogram. Alright, so the mass of the Pacific Ocean is somewhere around, let's just say 7 times 10 to the 11th kilogram. Alright, and let's say that the mass of this balloon plus gas is somewhere around 1 gram. That would be 1 times 10 to the minus 3 kilogram. Now you can quickly see, even without calculating, that the force of gravity on the Pacific Ocean from the Earth, that's around, let's see, 6.5 times 10 to the 12 Newton, while the force on the balloon of gravity, let's just call that F balloon, is somewhere around 9.82 times 10 to the minus 3 Newton. So why can a balloon happily go up in the air? Let's not consider something about density and buoyancy. Let's just look at the force of gravity. So if we had to something had to lift the Pacific Ocean up in the air, then you would have to generate a force greater than that of gravity. That is this 6.5 times 10 to the 12 newtons. Let's just say roughly 7 times 10 to the 12 newton. I think that's okay. In order to lift the balloon, you would have to generate this force. This force is doable. This force is not. So that is the general explanation from a gravitational point of view why a balloon can rise, but the ocean stay fixed.